Hello, my name is Samantha Ma and I'm from the University of Southern California. Today I'll be talking about deep learning segmentation of lenticulostriate arteries on 3D black blood MRI. I have nothing to declare. To give some context on the vessels of interest here, in this study we are interested in segmenting the lenticulostriate arteries, which I will refer to as LSAs. From prior cadaver studies, we know that the LSAs are small arteries on the order of 500 microns that branch directly off of the high-flow middle cerebral artery. As such, they are particularly susceptible to hemorrhage or occlusion, which could cause severe functional consequences. Early cerebral microvascular changes in conditions related to small vessel disease are particularly difficult to evaluate because these cerebral small vessels are largely inaccessible to existing clinical in vivo imaging technologies. Time-of-flight MR angiography at ultra-high field of 7 Tesla has been shown to enable the delineation of these fine perforating arteries on the order of a few hundred microns. However, as demonstrated previously, these vessels are often difficult to fully visualize in TOF images obtained using clinically available MR field strengths. As an alternative, we recently proposed a black blood MRI technique to observe LSAs with sub-millimeter spatial resolution using a 3D turbospin echo sequence with variable flip angle scheme, or 2-unweighted VFA TSC, at the more readily available 3 Tesla. Given the prior success of vessel tracing on TOF MRA images, we propose to develop and evaluate a deep learning-based algorithm to semi-automatically segment the LSAs from the 3D black blood images acquired at 3T. Regarding data collection, black blood images were acquired from 28 participants, 18 of which were female and ranging in age from 22 to 78 years old. All scans were performed on a Siemens 3T Prisma with a 32-channel head coil using the T1-weighted VFA TSC, or also known as a T1 space, sequence. The images had a resolution of 0.5 by 0.5 by 0.6, which was interpolated to 0.3 by 0.3 by 0.5 cubic millimeters, and they were acquired in about 8.5 minutes of scan time. In order to create a ground truth label for our deep learning model, manual segmentation of the LSAs was required. The LSAs were carefully segmented by hand in the black blood images by experienced and trained radiologists using the paintbrush tool in ITK Snap. Here we have the flowchart of the image preprocessing, the data input, the network training, and the evaluation of the deep learning models. As I mentioned before, black blood images were used for manual segmentation in ITK Snap. The 3D images and their labels were cropped to the subcortical region of interest. Then they underwent non-local means filtering to denoise the image, and then were split into hemispheres as a means to increase the sample size. The data input consisted of the non-local means filtered black blood images, the manual segmentation label as supervision, and an LSA regional mask, created by dilating all the manual labels and taking the common region to help the model localize the subcortical region of interest while avoiding other dark areas such as the ventricles. The dataset was then split into a training set and a testing set with 10-fold cross-validation. In other words, for each fold of the cross-validation, 9 groups of 10 were used as a training set, and the remaining 1 group served as a testing set. After training was repeated 10 times, the whole dataset was inferred and the 10 models produced 10 probability maps. The consensus map, or the average of the 10 probability maps, was then used for evaluation. For this study, we utilized the NiftyNet platform run with 2 NVIDIA GeForce GTX 1080 Ti GPUs to train 2 types of network architectures. Since this is a segmentation problem, we started with the conventional 3D unit architecture, but decided to primarily focus on optimizing the high-res 3DNet architecture, which offers a compact end-to-end 3D convolutional neural network structure that maintains high-resolution multi-scale features. The high-res 3DNet on the NiftyNet platform has 20 trainable layers with dilated convolution and dilating factors of 1, 2, and 4. For both networks, 48 by 48 by 48 volumes with a batch size of 4 were randomly extracted from the 3D preprocessed images for training. Volume level augmentation was utilized, including rotation and random spatial rescaling. The training process was performed with 30,000 iterations using dice loss and the atom optimizer. For comparison, vessel segmentation was also performed in MATLAB using 3D optimally oriented flux, or OOF, filtering to threshold the vessels in the image volume. OOF relies on image gradients to estimate local vessel orientations. In order to evaluate the model performance, we looked at several metrics comparing the model output with the manual segmentation label. First, for qualitative comparison, an error map with true and false positives and negatives was created. Next, we calculated the dissimilarity, the 95 percentile Hausdorff distance, and the average Hausdorff distance using the Evaluate segmentation software that came out of the Visceral project in Europe. The dice coefficient is a measure of similarity or elements in common between two samples. It ranges from 0 to 1 unitless values, where better performance is indicated by larger values. The 95 HD and AVD metrics represent the longest distances in voxels between two segmentation results and are generally resistant to outliers. Hence, smaller values would indicate better performance. Using 3D projections of the segmentation results from each method, we could produce qualitative error maps. Here we have an exemplary result from one subject. The manual segmentation label is shown in the first column and segmentation by OOF, 3D-UNet, and high-res 3D-net in the top row of the other three columns, respectively. The bottom row shows the error maps where red voxels indicate true positives, green voxels as false positives, and blue voxels as false negatives. Simply by visual inspection, high-res 3D-net appears to have achieved the highest performance. In the second example, the error maps illustrate the tendency for manual segmentation to miss the distal portion of the LSAs that deep learning and OOF can seemingly detect. OOF is very sensitive to curvilinear structures, but not very specific to blood vessels in the presence of CSF or other structures that may also appear dark in black blood images. As such, we can consider using OOF for pre-training the model for context, or as a starting point for future manual segmentation during pre-processing. Here we are looking at the box plots of the performance metrics for each segmentation method. As a reminder, for dissimilarity, better performance is indicated by larger values. On the other hand, for 95 HD and AVD metrics, smaller values indicate better performance. High-res 3D-net produced significantly superior performance compared with OOF and 3D-UNet for segmentation results relative to the manual segmentation label for all three metrics. The dissimilarity is still low at 0.54. But we attribute this to the high sensitivity of dice to even slight mismatches. As these small vessels are typically only 1 to 3 voxels in thickness, there is an imbalance for how many voxels are labeled as vessel versus not. In addition, the ground truth is limited by manual segmentation, which at best relies on what the human can see, and then very carefully paint on the monitor. Considering an average Hausdorff distance of less than 2 voxels, the high-res 3D-net deep learning model performed quite well. The results of the 3D-UNet and high-res 3D-net deep learning models are very promising, though the results should still be observed with caution because manual segmentation is limited to human interpretation. As shown, distal portions of the LSAs can often be missed. OOF filtering methods, though indiscriminate to other structures such as perivascular spaces or ventricles, are a sensitive, feasible approach to initiate the manual segmentation process, or even serve as pre-training data for future deep learning. With further hyperparameter optimization and a larger dataset, the high-res 3D-net model is our most promising method for specific LSA segmentation in black blood images. In conclusion, we presented an exploratory deep learning framework for the automated segmentation of LSAs from black blood images acquired at 3T. By using manual segmentation as supervision, 3D deep learning-based segmentation of LSAs was demonstrated to be feasible with relatively high performance. Currently, we are working to improve the generalizability of our high-res 3D-net model on black blood images from other scanners and sites by increasing our dataset size and fine-tuning the hyperparameters. We also aim to utilize the deep learning segmented vessels for morphological quantification, since the evaluation of the shape and number of LSAs may serve as a potential imaging marker of pathological conditions related to damaged LSAs. Finally, I would like to acknowledge the many people who made this work possible. Thank you to the volunteer participants, the LOFT group, and Loni at USC with all our collaborators. Lastly, this work was supported by grants from the NIH and AHA. Thank you all for your attention.